All right, so let's actually take this and put it to some practical use and do an actual graph. So what I'm stating here is that if you want to accurately graph a function using transformations, what we're going to do is first graph the parent function and generate a table of values to do that. And then we can just adjust the table using all of these transformations that we know. So I've already done the graph of this particular function just to save a little bit of time. But if we wanted to graph this from scratch, we would have to remember that the parent function means the function that uses only the operation for this function, which for us here is absolute value, and no other operations, no addition, subtraction, multiplication, division. In this case, the simplest function would just be y is equal to the absolute value of x. Okay, so if I ask you to graph the parent function to generate a table of values, you're just going to plug -2 into the parent function, not the transformed one. So I'm going to say if I plug -2 into the parent function, it says the absolute value of -2, which is 2. Plug in a -1. The absolute value of -1 is 1. When I plug in 0, I get as absolute value of 0, the absolute value of 1, and the absolute value of 2. So if you graph those points, that's how I generated this particular graph. 1, 1, 2, 2, -1, 1, and -2, 2. And you could keep going with the list, but you get the idea. We get this nice V-shaped graph. Okay, so what we're going to do is we're going to take each of these points and we're going to transform them using what we know about BCAD, black cats and dogs, and how they affect each of these x and y values. Right? So I'm going to take this point, -2, 2, and I'm going to look at my values, and it says, okay, remember the idea is BCAD, MA, MA. Okay, and the B and the C affect the x's, and the A and the D affect the y's. Right? So we get something that looks like this. Okay, my handy little chart here. So I'm going to look at this first and say B value. Don't see a B value because there's nothing being multiplied inside of this function, so we don't have to worry about that and its reciprocals. Okay, I do have a C value of 1, so this says add C to the x part of the point. So instead of this being -2, I'm going to add to the x part of the point, and it's going to become -2 plus 1, which is -1. I'm going to do that for all of these because I'm done with x. Right? B and C are the only things that have affected x. I've done both of them. So really the summary is the only thing that's going to change for all your x points is you're going to add 1 to all of them. So this is going to become 0, 1, okay, 2, and 3, right? All of the x values just got 1 added to them. Okay? So now let's talk about where the y values end up. So remember we say y is affected by a and d. I have an a value and a d value. Okay? So let's talk about what they do. This says multiply a by the y value, right? And then add d to the y value in that order. So be careful about the order. Multiply a by y and then add d to y. So if I were to do that, this says times 2 plus 2. Times 2 plus 2. So if I take the y coordinate and do times 2, I get 4, and then add 2, I get 6. Okay? If I multiply this by 2, I get 2, and then add another 2, I get 4. 0 times 2 is 0. 0 plus 2 is 2. Okay? 1 times, we've already done this, 1 times 2 is 2 plus 2 is 4. Okay? And similarly, 2 times 2 is 4. 4 plus 2 is 6. So I'm claiming that after the 3 transformations, a C value, an A value, and a D value, -2, 2 is going to end up at -1, 6. And the same is going to be true for the rest of these. So this is pretty much the same as what we did in the last video when we were just worried about 1 point. We're just doing it 5 times. So what I'm going to do is take each of these points and graph them. If they said graph this new function, what I'm claiming is that -1, 1, 2, 3, 4, 5, 6. Okay, 0, 4, which would be right 1, 2, 3, 4. Okay, 1, 2, 2, 4, and 3, 6 would all be on my graph. So if I were to graph this one, I'll try to draw as straight a line as I can. Okay, it's still, if you notice, looking like the parent function. It has the same shape. It's still a V because all absolute values will look like that. But if I were to describe in words what happens with these 3 values like we did on the very first video, I would say, well, C does a slide to the right, D does a slide up by 2. So if I were to look at that, like my original point here, right, my origin point, the vertex, went to the right by 2. I'm sorry, to the right by 1 and up by 2. That's exactly how I would describe this in words. I would say C means go to the right by 2, D means go up, or let's try that again. C means go to the right by 1. D means go up by 2. And that's exactly what happened to my vertex. Okay. A is a little bit trickier because we've been describing it as grabbing the function and pulling it on the top and the bottom and making it stretch. So the effect that ends up happening is really that it gets skinnier. We can actually check that this is making sense because if you notice, between these 2 points right here, I only have a space of 2, whereas I used to have a space of 4. Right? So you can actually see that they're getting closer together. Right? So if you want to check that you actually did your A value correctly, here's what vertically stretching actually means. If I were to count the space vertically, meaning going up and down, between my points, it's always a space of 1. So if you notice, for me to go from my origin point up to the next row of points, I only went up by 1. Right? So I did an up by 1, and I do another up by 1, and I can find some points, and I could continue that trend. Now if you notice in my new one, I doubled it. I went up by 2, and I went up by 2, right? So what that effectively does is it spaces the points out on the graph by whatever the factor is. So if I had a 3 here, this would have gone from 1, 1, 1 to 3, 3, 3 before, and so it's effectively spacing them out a lot more. Okay, and if I had a fraction or a decimal, it would be the opposite. Instead of it being 1, they only might be a half a unit apart or a quarter unit apart or whatever the case may be, and so it's actually going to shrink them in. Right, so that's the effect that these functions have, and this applies to any functions at all. We used an absolute value example, but we could do this equally for quadratics or cubics or any other type of function.